The most basic type of experimental design is what's called a completely randomized design. So what are some of the elements? Obviously, you have your subjects or your guinea pigs. And remember, we talked about how important random assignment was. So you need to do that. Subjects don't get to choose their treatments. You must randomly assign them to the different groups. Here I only have 2 groups, but you could have quite a few groups if you needed them. But it's important to create groups. Don't have individual 1, individual 2, individual 3. And the reason is we need to be able to distinguish the results and make sure that it's not just chance creating that. So by having groups and increasing our sample size here, we minimize the effects of just plain old chance. So once you've established your groups, you assign treatments to them. And you do, by the way, one of these could be no treatment at all. So you typically have a control group that you keep normal, status quo. And part of this is you're trying to keep all the other variables the same for all your groups. And if you have a control group, that helps with that. Once you're done, you basically measure your results and you compare your response variable. So what does this look like in real life? This is an article that just came out, a possible cure for peanut allergies. And this is interesting to me because I know I have students every year who have peanut allergies and they have to have EpiPens and things like that. So this is a big deal in the US right now. And in the UK, well, actually the UK reported that there's a breakthrough new treatment for peanut allergies. And it was an experiment. It was a team at Murdoch Children's Research Institute in Australia, and they assigned 56 children with peanut allergy to receive a daily dose of either the probiotic protein combination or a placebo. And at the end of 18 months, 82% of those given the treatment had gained tolerance to peanuts, compared with only 4% of the placebo group. So first of all, let's talk about placebo. A placebo effect was noticed by Dr. Henry Beecher back in the 1950s. He looked at 26 studies involving placebos and found out that even taking a sugar pill is helpful to about 32% of patients. Kind of like when we were little, fell and skinned our knee and we asked mom to kiss the boo-boo and we felt better. So the placebo effect is kind of similar. When you get a pill, you're like, okay, I'm going to feel better now. And it works for 32% of people. All right. Now, how do we combat? Oh, by the way, this is not intentional by the people. It's just unconscious. It's sort of natural. So it's not them being bad. So how do we combat that effect? We use something called blinding. Either the individual receiving the treatment or the person recording the results does not know which treatment is applied. So usually we could say sugar pills are given to patients, that would be the placebo, and you can't even tell. If the patient can't tell which is which, that's called single blinding. And if both the patient and the person recording the results can't tell, that's actually called double blinding. By the way, no treatment does not count as a placebo because you can tell when you're not getting treatment. Now, there is sort of an exception. There is, let's say you were looking at fertilizers for plants, right? The plants aren't really going to be affected by the placebo effect, but it could be if you're the person measuring plant growth and you know which ones received the fertilizer, then you might be more optimistic when you're measuring by accident. So that would be a case where you blind the measurer, the person recording the results, and not worry so much about the individuals in the study. So let's go back to that peanut allergy experiment. So first of all, the subjects are 56 children with peanut allergies. Not just 56 children, but 56 children with peanut allergies. So we're going to do random assignment. And we can number the children with unique numbers. In this case, I did 01 to 56. Probably would have been better to do 00 to 55. Outcome is 2 digits on a random number table or from a calculator, or it could be a computer, some sort of random number generator. I'm going to ignore repeats because I'm not going to reassign the child to the group twice. The child only gets to be in the group once. And I'm also going to ignore outcomes outside of my range. I'm going to stop when I get 28 students for the first treatment group. That gives me the replication. 28 students will help account for random variability. So now I've got my two groups of 28 children. One of them is receiving the probiotic protein combination, and the other is receiving the placebo. So then we measured their results, and that's where we saw the 82% that gained a tolerance and the 4% that gained a tolerance. Now let's take a look at my experiment where I was looking at grading. So I've got 80 geometry students. I could do random assignment. In fact, I want to do random assignment. So I'll number them 00 to 79 and ignore outcomes above that and ignore repeats. And the outcome is 2 digits from my random number table or generator. Stop when you get 40 students for the first treatment group. So there are my 40 students split up. 40 in the first group, 40 in the second. One of them I can use automated grading. The other I could just hand grade. And then I'm going to measure their DCA performance and compare results. Now, one thing as a teacher is my students might say, hey, I really prefer that I don't like to use the automated grading. I'd rather just do it on the paper. Can you hand grade it? Technically, that would violate the experiment. So voluntary choice is always bad for any experimental design. It doesn't matter which